I share with you guys telescoping series. Technically, not on the AP exam, but you know what? It's bonus coverage. It's wicked cool type of series because it's just another series that we can find the sum of. It's other if we don't talk about telescoping series, the only series you can find the sum of is a geometric series. So I'm going to give you a quick video here on what a telescoping series is. So here is a sum. Check it out there. Right down there. Half plus a sixth plus a 12th plus a 20th. Now, at first glance, you're thinking, well, let's just see if it's geometric. If I'm asked to find the sum, it's got to be geometric, right? Well, not exactly. There's not a common ratio, so can't use the geometric series for this. So we could look at it two different ways. One way is to look at the partial sums. So let's look at that. So if we look at the partial sums, we can add up the first term. Well, that's a half. You can add up a half and a sixth. You get 2/3 when you do that. You can add up a half and a sixth, which is 2/3, and then the next one, which is a 12th. And 2/3 plus a 12th is 3/4. And if you add 3/4 to a 20th, you get 4/5. So, hey, the jig is up here. I think we know what's going to happen. For any n value, the sequence of partial sums is n over n plus 1. That is an explicit formula that describes what the partial sum sequence does. At infinity, the partial sum sequence then would converge to 1. And since the sequence of partial sums converges to 1, well, the series does too, because the series and the sequence of partial sums are one and the same. So that's pretty cool. All right, so maybe let's look at a different way. Another way to look at it, right? I talk about the partial sums here. What if we look at the partial fractions? See what I did there? Yeah, pretty smart, huh? All right, so the partial fractions, if we dig deep into the recesses of our mathematical history, we know how to deal with partial fractions. It was a way to deal with, it was an integration, not technique, but an integration idea, just to manipulate through algebra with partial fractions. So a half plus a sixth plus a 12th, same series we saw before. But now if we look at those denominators more carefully, those denominators are the product of consecutive integers. 1 times 2, 2 times 3, 3 times 4, etc. You can actually write a sequence of terms here, like each term individually is 1 over n times n plus 1. Okay, so each single individual term looks like something that we could use partial fractions to separate. And we can't. I'm just going to magically, poof, 1 over n times n plus 1 is 1 over n minus 1 over n plus 1. It is a check. So the sum from 1 to infinity of 1 over n times n plus 1, which would be that original series I told you about, is the same as the infinite sum from 1 to infinity of the partial fraction decomposition piece, 1 over n minus 1 over n plus 1. So looks like we've just done more work for ourselves here, right? Not so. Because now if we write out the individual terms using this partial fraction approach, the first term, when I plug in 1, is 1 minus a half. Then the next term, when I plug in n equals 2, is a half minus a third. And then when I plug in n equals 3, I get a third minus a fourth, and a fourth minus a fifth, and a sixth, blah, 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 and it just keeps going and keeps going and keeps going. And you already notice that there are some pairs that cancel out. In fact, with these 4 terms that I've listed here, there are pairs that cancel out, and then there is a pair on the front end and the back end that don't cancel out, the 1 on the front end, and then that 1/5. It doesn't mean that this is 1 minus a fifth. It just means that this 1 term at the front is going to have a remnant term on the back end of the series. And what's happening to that remnant term on the back end? Well, the more terms we write out, the smaller that little critter becomes. So that little piece there on the end that you see as -1/5 is going to be -1/6, and 1/7, and 1/100000th, and 1 millionth. Well, yeah, millionth, and then 1 billionth, and then 1 quadrillionth. And it's going to be so tiny as to effectively be nothing, which means that the series is going to converge to 1. And now that canceling out like that, that's why this is called a telescoping series. If think of a pirate telescope, right? That shrinks, and they can draw it out so they can see far away, but then they can shrink it up, put it in their pocket, or give it to their parrot or something like that. I don't know. But it's called a telescoping series. So let's look at some things about a telescoping series. So that happens when you get these terms that cancel out. It's called a telescoping series, what I wrote down there. So I talked about the pairs, right? And the remnant terms on the tail, the remnants on the tail end of the telescoping series. If those remnants at the back end approach 0 or approach a value of any kind, then the series is going to converge. However, if the remnant terms at the tail end don't converge, like say they go to infinity, then that tells us that the telescoping series will end up diverging. So it's not true that all telescoping series converge, just most of them. There's actually going to be another tool that we have outside of telescoping series that will be easier to determine converge or diverge for series that will end up telescoping. But it's cool to look at them this way because you can actually answer that second main question, like, does it converge? Here's a test that I can apply. But this will actually allow us to find the sum, which is kind of cool. That's what we're talking about in this series of videos. So a telescoping series sum is going to converge only if those remnant terms, those back end terms, converge to a value. Usually that's going to be 0. And if the remnant terms approach infinity, then the telescoping series diverges. All right, so I'll give a couple examples here, and then we'll wrap this extra video up. So here is the sum from 1 to infinity of 1 over n plus 1 minus 1 over n plus 3. And you can see kind of already how there's like a thing minus a thing that's going to come later. Like eventually the n plus 1s will become n plus 3s on down the line. So you can see there's like a give and take kind of with these positive and negative pieces of that sequence there. And really what I like to do is I like to just write it out. If there's a constant that maybe I can pull out, that's what I like to do, factor that out. Like if there were 2's in the numerator or 5/3 in the numerator, just factor those out. But here in this one, you can see I wrote this out. You get 1, whoops. Go ahead and scratch off that first term there. We actually don't need that first term, right? That first term shouldn't be there. So let me see if I can quickly sketch on there. Yeah, this little term shouldn't be there, right? Because we're starting at n equals 1. So when n equals 1, the first term is a half minus, well, daggone it. This whole critter is now wrong because I goofed when I wrote this. So let's maybe start from scratch. So the first term, 1 over n plus 1, would be a half, right? So a half minus a fourth. And then the next term would be a third minus a fifth. And then a fourth minus a sixth. And then a fifth minus a seventh, etc., etc. You can start seeing what cancels out, right? So the positive 1/5 and the negative 1/5. That's a positive 1/4. Hey, y'all were yelling at me to change that, and I knew it was happening. I just, okay, the positive 1/4 and the negative 1/4. So let's see what survives. The surviving pieces of this is the 1/2 and the third, but then you got these little tail end remnant terms that are just hanging on for dear life. But they're going to eventually, you might see, they'll waste away to nothing because there are more terms that I write out. Those terms will get smaller and smaller. So those remnant terms go to 0. The first terms at the front, a half, and a third. Let's see, we add a half and a third together. It's 3/6, then 4/6, 3/6, and 2/6, 5/6, right? Is what that sum would be. All right, sweet. All right, here we go. So let's continue along the road here. Now this is going to be bogus right here because I'm a goofball and I can't add numbers. So it doesn't go to 3/2, it goes to 5/6. We showed that. Let's quickly move on to another one. Nothing to see here. Okay, let's evaluate this next one. The sum from 1 to infinity of log of the quantity k over k plus 1. So this one, again, log of k over k plus 1 at infinity, right, is like natural log of 1, and the natural log of 1 is 0. So you might be tempted to say, well, it's going to converge. That series that right there is going to converge because each the terms in the sequence there go to 0. But that tells us nothing, right? The nth term test, that's the false nth term test. The nth term test says that if the sequence terms don't go to 0, then you know the series diverges, nothing else. So if the sequence values do trend to 0, you don't know anything, really. So here we go. Yeah, false nth term test. See, I knew it was coming, right? It's all there. Look, check it out. It was all right there. Told you that. So we're going to use some properties of logarithms to break that apart into the log of k minus the log of k plus 1. And if you don't remember the natural log properties, then you should. So you can sniff out the telescoping behavior here. We got log of k minus log of k plus 1, like k and k plus 1, they're going to eventually turn into one another. So again, let's write it out. It's always okay to write it out. So that's going to be log of 1 minus log of 2, log of 2 minus log of 3, log of 3 minus log of 4, and so on and so on and so on. Cancel, 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 cancel. And everything's left except for the first term, natural log of 1, and then the last term, the remnant term, natural log of some big, huge number k. And as k goes to infinity, the log of infinity is infinity. So log of 1 is 0 minus this big, huge number. It's actually going to infinity. It's going to diverge as a series. All right, so you saw a telescoping series converge. You saw a telescoping series diverge. Again, it's not on the AP exam, but it's worth a look because it's kind of fun to talk about. So that concludes lesson 6.1. We talked about nth term test. We talked about geometric series in the last video, and now this last bonus coverage on telescoping series. So stay tuned. Next time, we're going to start getting into some different tests just to prove convergence and divergence, not to discuss what the series converge to, but just some tests that say whether a series converges or diverges. So stay tuned for lesson 6.2. Peace. Oh yeah, don't forget to smash that like button, hit the notification bell so you get all the fresh content from calculus. Yeah, baby.